So we are looking at section 2.4, rates of change and tangent lines. So this is your first introduction kind of to calc and derivatives. So our goals for the day are to find the slope of the secant and the slope of the tangent line. So in order to find their slopes, we need to know what they are. In order to know what they are, we're going to start with something we do know. We know what an average rate of change is. An average rate of change is the amount of change of a quantity over a period of time. It is the amount of change of a quantity over a period of time. So it's change over time. So oftentimes this is kind of like distance equals rate times time, where you're solving for rate. So it's the change in the distance over the change in time, or average speed. Percent per year. Average monthly rainfall in inches per month. Miles per hour. So this is those per problems, where you get the amount of change of a quantity over a period of time. So if it says find the average rate of change of a function x cubed minus x over the interval 1 to 3, well, the 1 to 3 is kind of like your change in time. So it's going to be the denominator. And then what we do is the change in quantity would be f of 3 minus f of 1. So change in quantity over change in time. But again, now we're talking about a function. So change in the function over the change. So f of 3 is 3 cubed minus 3 minus f of 1, which is 1 cubed minus 1, all over 3 minus 1. So 3 cubed is 27 minus 3. 1 cubed is 1. 1 minus 1 is 0. So it's kind of like minus 0. 3 minus 2, or 3 minus 1 is 2. So 27 minus 3. 24 over 2, or 12. So the average rate of change of f of x over the interval 1 to 3 is 12. We can also describe rates of change by looking at slopes of secant lines. So we can describe rates of change by looking at slopes of secant lines. And what they approach is the slope of the tangent. So the slope of the secant helps us find the slope of the tangent. A secant line to a curve is a line that passes through 2 points on the curve. So what we do is we find the slope of a secant line by using the equation n secant equals f of x2 minus f of x1 all over x2 minus x1, which really just looks like the equation of slope. Because f of x2 is a fancy way of saying y2 minus y1, right? So fancy way to say slope, y2 minus y1. So the slope of the secant is really just the old school way we found slope. Old school slope. The slope of the tangent is the calc way. So what we're going to do is take the idea of the old method, which is the slope of the secant, and apply that concept to help us find the slope of the tangent in calc. A tangent to a curve is a line that touches the curve at 1 point. A tangent to a curve is a line that touches the curve at 1 point. We find the slope of a tangent line by looking at the limit of the slope of the secant line. So the slope of the tangent is equal to the limit of the slope of the secant. So here we have a graph, and this graph is a depiction of the slope of the tangent and the slope of the secant. So it says in the graph below, we are trying to find the slope of a tangent line to the function at the point a, f of a. In order to do this, we must choose another point so we can calculate the slope of the secant line. We will choose this point to be h units to the right of a, f of a. So we have a plus h and f of a plus h. So here's my a, f of a right here. And then we chose a second point, h units to the right. So we'll call that second point f of a plus h. So we've gone h units to the right and f of a plus h minus f of a units up. So that red line is the slope of the secant. It's the secant line. The tangent line is the blue line that we are trying to find using the secant. So same graph, it's just now what we're going to do is look at the equations we've constructed. So the equation for the secant line becomes the slope of the secant equals f of a plus h minus f of a all over h. So the slope of the secant line becomes f of a plus h minus f of a all over h. What we're going to do then is apply a limit to find the slope of the tan. So the slope of the tan is the limit of that secant slope where the denominator is going to 0. So what we're trying to do is we're trying to make h incrementally small units away from a. So over in the graph, h looks like it's really far away. But really, by making the limit as h approaches 0, we're making the distance between them incrementally smaller. So what we're doing is we're trying to get that h down to almost 0. So we're making the a plus h distance away from a incrementally small by making the limit approach 0. This formula is called the difference quotient. So you might hear or read in your notes the words difference quotient. So this is the difference quotient. So in example 1, experimental biologists often want to know what the rates of which populations are growing under controlled lab conditions. So not like your house. Although I think this is true in our house too. The following points represent how the number of fruit flies grew in a 50-day experiment. I hate fruit flies so much. They're so gross. They get everywhere. So it says using the points 23 and 150 and the points 45, 340 from the graph given, compute the average rate of change, aka our new slope of the secant line, created by these 2 points. So what we're going to do is we're taking this point on the line here and this point on the line there, and we want to find the slope of the line between them. So we are trying to find the slope of this line right here. So how do you find slope? You pick 2 points on a curve, and you find the distance between them. So we'll take 340 minus 150 over 45 minus 23. So you take the 2 points, and you find the difference between them. So 340 minus 150 is 190. 45 minus 23 is 22. So what that means is we looked at 22 days, and we looked at the change of the fruit flies over those 22 days, which was 190. So if you reduce that, you get about 8.6. So what that means is about 8.6 fruit flies per day. So the change was 8.6 fruit flies per day. That change can be called the average rate of change. And remember now, average rate of change is the long definition for slope of the secant. So the slope of the secant for the average rate of change is 8.6 flies per day. So as you look at this curve, what do you think about the slope of the secant line we got and the actual rate of change of the fruit flies at 23 days? Does our prediction that that slope is 8.6 seem pretty good? Or is that line not quite as steep as the curve looks at day 23? So that's what you have to ask yourself. How far away is 22 days? 22 days is a pretty big difference in terms of population growth. So what we want to do is we want to shrink the number of days that we're looking at from day 23 to the population growth we're looking at. So maybe now we look at 35 days. So we're going to compare day 23 to day 35. So you have to go to your graph, and you got to kind of predict. So at day 35, I'm predicting, I don't know, I like nice numbers. So maybe I pick 310. So you take 310 minus 150, so you get 160, and 35 minus 23 is 12. So 160 divided by 12 is 13.3. So now, is my line steeper or less steep than the first line? Well, what slope is greater? 8.6 or 13.3? So 13.3. So does this black line now look better at predicting the slope of the blue curve than the first black line? Yes. No, there's only you. But like, it does, right? Like, it looks better. It looks like it hits the curve even closer. What happens if I get even closer in days? So now, let's not compare 35. Let's compare 25. So day 25, I would predict maybe that population is almost like right in the middle, right? It's like 175. So now I'm only 2 days away. 175 minus 150 is 25 over 2 days. So 12.5. Did we nail the slope of the line? I think so. Looks pretty good. Looks like it's right on top of the blue between those 2 points. So our prediction going 2 days later is 12.5. Let's go with 2 days prior. So if we compare to the left, we always like to compare to the right. So let's compare day 21. Let's do 20 so we know we're more. So we're 3 days away, still pretty close. We know at day 23, it's at 150. So on day 20, it looks like it's at 100. So you get 50 over 3. So 3 goes into 50 somewhere about 16 times. So when I look at that, it looks a little bit steeper, but still pretty close. So we are going to say between the 13, the 12.5, and the 16, that the rate of change is not that 8.6 we got the first time. That was just way too far away. That slope is just way not close enough to what we are looking at. So I would say our average rate of change of fruit flies is probably about 13. Because again, we can't have half a fruit flies per day on the 23rd day.
Good question.
Yeah.
When you get closer to the initial day that you're working from, don't you lose a bit of variability that could fall later on in the graph that would affect it?
That's why, yes. And that's why we kind of looked at all the different ones. So we don't just pick one. We gotta pick like a little bit below, a little bit above. So you can like, so that's where like the 16 and 12.5, that's why I went with like 13. A little higher than this, a little lower than that. You could have picked 14 even too. You're gonna go right smack in the middle. But yeah, you don't want to ever just look at one. You want to go to both directions. Because you never know. Somebody might push one, somebody, great. It's not, if it's controlled as an experiment can be, but no experiment is perfect. So that's the practical application for average rate of change. Let's look at the algebraic. So it says find the equation of the tangent lines, and now we're looking at limits to the parabola y equals x squared at the point 1, 1. So we'll start with the slope of the secant. So the slope of the secant is f of 1. So we're going to always plug in, this is kind of like my a, f of a. So the slope of the secant would be f of a, which is 1, plus h, minus f of a, which is 1, all over a plus h minus a, so it always ends up just being h. So the slope of the secant is f of 1 plus h minus f of 1 all over h. So what is f? Well, f is really just the fancier way of saying y. So what we're going to do is we're going to plug 1 plus h into our function. So you get 1 plus h squared minus 1 squared all over h. So 1 plus h squared needs FOILed out. So first is 1, outer is h, inner is h, plus h squared. 1 squared is 1, all over h. 1 minus 1, cancel out. So you get h plus h, which is 2h, plus h squared, all over h. So if I have h squared and an h in the denominator, I can cancel one of each. So I get 2 plus h. So what that means is the slope of the secant is 2 plus h. Now, it said find the equation of the tangent line at a point. So in order to find the equation of a tangent line, I need the slope of the tangent. The slope of the tangent is equal to the limit as h approaches 0 of the slope of the secant. Well, we just said the slope of the secant was 2 plus h. So we're going to say the limit as h approaches 0 of 2 plus h. When you plug in 0, and we get 2. So the slope of the tangent at 1, 1 is 2. The slope of the tangent at point 1, 1 on the curve x squared is 2. The equation of a tangent line comes from the point slope form. So we do y minus y1, or f of a in this case, which is 1, equals the slope of the tangent, which is 2, times x minus x1, which is 1. So it's kind of like y minus f of a equals the slope of the tangent, x minus a. So here's our answer. So the equation of the tangent line is y minus 1 equals 2, quantity x minus 1. The flaw in all of this is your textbook is going to put your answers in slope intercept. So in order to check them in the back of the book, we have to change it into slope intercept. So lots and lots. Let's try again.
Quick question.
Yeah.
How did you know to put f of 1 plus h into the...
That is the formula for slope of the secant. So the basic formula for slope of the secant is f of a plus h minus f of a all over h. So that is the slope of the secant.
Okay.
Yep. So you're okay. So it says, now find the exact slope of the tangent line to the function y equals x squared at any point. So in the previous problem, we found it at the point 1, 1. We can actually find it at the point A, or any A, in the whole problem. So what we're going to do is take the limit as h approaches 0 of f of a plus h minus f of a all over h, where f is x squared. So we plug in a plus h and plug in a into our function that we are finding the slope of the tangent. So a plus h squared becomes a squared plus 2ah plus h squared, coming from our Pythagorean, our Pascal's triangle, where it goes 1, 2, 1. So you have a squared plus 2ah plus h squared minus a squared all over h. Cleaning that up algebraically, a squared minus a squared cancel. So you're left with 2ah plus h squared all over h. So once again, we have a GCF of h up top. So you can take out that GCF, leaving you with 2a plus h all over h. So my h's cancel. Once the denominator is no longer there, we can plug in our limit. So, the slope of the tangent for the function y equals x squared is 2a. So what that means is I could say, find the slope of the tangent line to the curve x squared at the point x equals 5. And now you could find that slope just by plugging 5 into a. So this is like, in general, the slope of the tangent to the curve x squared will always be 2a for any point a on x squared. Slope has several equivalent statements. So we have several ways we can say the word slope. We can say y equals f of x at x equals a. We can say the slope of the tangent to y equals f of x at x equals a. The instantaneous rate of change of f of x with respect to x at x equals a. And that's the key word, is tangent is instantaneous. Tangent is instantaneous. Secant is average. Tangent is instantaneous. Tangent is instantaneous. So again, all of these equivalent statements are a way of expressing the slope of the tangent. All of these are ways to express the slope of the tangent. All of these are equivalent statements for the slope of the tangent. So let's do another exploration for slope of the tangent. It says find the slope of the curve at x equals a for f of x equals 1 over x. So again, same idea. We are finding the limit as h approaches 0 of f of a plus h minus f of a all over h. Anytime they ask you to find the slope of a curve at a point, that's what we're doing. So in this case, f is 1 over x, so I get 1 over a plus h minus 1 over a all over h. And again, since we're looking for the slope, we need the limit. However, what do I know about subtracting fractions that have unlike denominators? In order to subtract fractions, they have to have the same denominator. So what that means is we need the least common multiple for the LCM of a plus h and a. So that's a plus h. So what we got to do is we need to create a common denominator for those two fractions. So that means on the left, we have to give it an a, and on the right, we have to give it an a plus h. So we get a over a plus h. So multiplied by a over a. And on the right, we're going to multiply by a plus h over a plus h times the already there a. So now we have an LCM. So by having an LCM, we can group the numerators together. So we have the limit as h approaches 0 of a minus, now that negative has to distribute to both the a and the h, because it's really like minus quantity a plus h. So a negative is going to distribute in to both. And this is all over a plus h, all over h. So holy moly, fraction and fractions, distributing negatives, algebra. It's all algebra. All watching your signs, taking your time, and not losing anything. So I have a minus h all over a plus h, all over h. So what's super nice is the a's cancel. How do I get rid of a fraction in a fraction? Well, you multiply by the reciprocal of the denominator. So we're going to multiply by 1 over h. So we got negative h all over a plus h times h. What happens? My h's cancel. So I'm left with negative 1 over a times quantity a plus h. So I'm going to plug in a 0. So I get a plus 0. So a plus 0 is a times a is a squared. So you get negative 1 over a squared. So the slope of the curve at a for 1 over x is negative 1 over a squared. So it says, where does the slope equal negative 1/4? So not what is the slope at negative 1/4, but where does the slope equal negative 1/4? So slope is negative 1/a squared. We want to know what a value will make it negative 1/4. So we're going to set that equal so I could solve for a. So you get negative a squared equals negative 4 just by cross multiplying. So divide by negative 1. You get a squared equals 4. Here's where you got to be cautious, because now we have something squared. We take the square root. So when I take a square root is when my answer gets the plus or minus. So I get a equals plus or minus the square root of 4, which is 2. So the slope will equal negative 1/4 at 2 points. At positive 2 and negative 2. So again, that's like our x value. So you can find f of 2 and f of negative 2 to get your coordinate points. So the slope of the tangent will be negative 1/4 at both 2, comma half, and negative 2, comma negative a half. So the slope of the tangent will be negative 1/4 at 2 and negative 2. Last question. What happens to the tangent to the curve at the point A, 1/a, for different values of a? What happens to the tangent to the curve at the point A, 1/a, for different values of a? Well, let's talk and work through this. So the first thing we want to do is think about the slope of the tangent. So the slope of the tangent negative 1/a squared. So the first thing I see when I look at that is that the slope of the tangent is always negative. There is no way for the slope of the tangent to be positive. A squared is always positive, so a negative over something positive is always negative. So the slope of the tangent is always negative. Slope of the tangent is always negative. So what does that mean? Well, it means that as a gets really, really close to 0, so let's say we want to talk about the limit as a goes to 0 for negative 1/a squared. Well, since it's always negative, the slope as we get closer and closer to 0 would be going where? This is if right? It's fair to say we have a vertical asymptote at x equals 0, or at a equals 0 if you don't want to use x because I'm starting to mix the variables. But we have a vertical asymptote at 0. If the slope of the tangent is always negative, the vertical asymptote is also always going to negative infinity then. So as a goes to 0 from the right, the slope goes to negative infinity. So the slope is getting really, 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 really big as we're going to 0 from the right. So the tangent will become increasingly steep. So what that means is this line is super, 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 super steep. And we can say the same as a goes to 0 from the left. The slope is going to get really, really, really horizontal as well. So again, this graph will be coming up from negative infinity from both the left and the right. So again, it's approaching negative infinity on this side. And then think about it as, yeah.
Sorry, how do you know that it's doing that and not opposite?
Because no matter what I plug in, this negative right here is going to force my answer to be negative infinity. No matter what, like if I plug in -1 or +1, it'll always be negative because of the negative slope.
Okay.
Like just because there's a negative in front of the function and a squared, the sign will always be negative. Because no matter what you plug into a squared, it's positive, but a negative times positive is always a negative. Does that make sense? Okay. That is it.